Uh, Good afternoon, students. Today our class is on wave function and its significance. So, what is wave function? Uh, Mathematically, we have if you want to represent a line, a circle, or a curve, we define mathematically with a function f of x, which is y is equal to mx plus c. We is usually used to represent a circle. Similarly, x square plus y square is equal to a square will represent a circle, and x square by a square plus y square by b square is equal to 1 will represent a ellipse. So, what is the significance of f of x in defining these things is that it depends upon whether the physical object is in a linear motion or in a circular motion, or it is sweeping a curve, etc. like that. Okay, so this means that f of x describes how the particle is moving in a particular boundary, or in other words, f of x simply gives the entire information regarding the system or the particles in the system in which they are behaving. So in the similar manner, if you consider any quantum mechanical system, and in a quantum mechanical system we should define that the wave like motion of the particle, and in order to express that mathematically, we take or we consider, is not similar to f of x, we consider a function, is not in mathematics to define any curve, or if you want to plot anything, we will consider f of x. Similarly, here also we'll in a quantum mechanical system we'll define the wave like motion of a particle confined in a quantum mechanical system by a wave function. Okay, so what exactly the wave function is? The wave function helps us to trace the trajectory of the wave. Generally it gives the potential variations at any particular instant of time. As we know, according to de Broglie hypothesis, electrons behaves both as particles as a wave, that is wave particle duality. So if the electrons are behaving as a wave, there must be a wave equation to describe how they behave. Similar to how if a particle is confined to move in a straight line, we will represent in terms of y is equal to mx plus c, or if a particle is confined to move in a circle, is not of radius a, then we will represent it in the form of x square plus y square is equal to a square. So similarly, if the electron which has wave particle duality, so how the wave associated with an electron will behave should also be represented mathematically. So that function which defines or which exactly gives the characteristic of a particle mathematically in a quantum mechanical system is being termed as a wave function. So the value of wave function of a particle at any given point of space and time is related to the particle's is related to particle existence at that particular instant of time. So f of x is used to represent mathematically in the similar way how a wave function is being represented. It is represented with a Greek word called as psi. Psi, a Greek word psi. So the psi square is not the square of the wave function, that is psi square has a physical significance, and we'll come across with that in the next one. In deeply, if you want to know about what is exactly the wave function, so a wave function which is represented by psi is being associated with a moving particle. It is not an observable quantity, that means it is not similar to quantity which can be observed, but the existence can be defined, so it does not have a physical meaning, but the significance is very important. How the psi will defines the wave function of an quantum mechanical system. So for that purpose, the psi in general is being considered as a complex function. So psi, isn't it? That is a complex function is being defined, is in general can be written as a plus ib. So psi of x, y, z and t. X, y, z are dimensions and t is time. So when you come across with a quantum mechanical system, and if you assume there exists a particle within that quantum mechanical system, so now if you want to define what is the wave particle duality of that particular particle which is existing in a quantum mechanical system, we have to define its behavior with a mathematical form, and that mathematical representation or a wave particle the wave-like motion of a particle in a quantum mechanical system is given by wave function. So in general the wave function is being treated as a complex function which is written as a plus ib. So since it is a complex function, it does not have any physical meaning, so that's why we will consider the complex conjugate, that is the complex conjugate of psi, that is represented by psi star, which is a complex conjugate, that is a minus ib. So that the product of psi and psi star, that is psi and psi star, psi and psi star, which is given by a plus ib into a minus ib, that is equal to a square plus b square. If you solve it, you will come across with a square. Here a square plus b square will give you a real quantity, whereas individually psi, which is a plus ib or psi star a minus ib, will does not give an exact value, but psi star will gives you a real quantity. So that means we cannot directly measure psi, but the product of psi with its complex conjugate, that is defined as probability density, is used for locating the particle at a given instant of time. Okay, so the positive square root of psi star, that is given by modulus of psi. So the probability p, that is modulus of psi star psi, that is simply called as modulus of psi square, is defined as a probability density. So what this probability density will gives you, isn't it? What exactly it means? See, this is the probability density. So the square of wave function which gives the probability density of the particle. The value, if the more the value of the probability density, the more likely the particle will exist in that particular region. So p, which is represented at modulus of psi square, which is in general is written as in the form of volume integral minus infinity to plus infinity psi star psi dx dy dz. So this dx dy dz can be simply called as d tau, which gives you volume term. So this equation can be modified as integral minus infinity to plus infinity psi star psi d tau. So this will gives you probability density. So probability density will gives you what? The probability of finding a particle in a quantum mechanical system at a given instant of time. Now if I consider a particular boundary which has limits from a to b, and I assume a quantum mechanical system within that boundary, so that I may expect a particle exists in that particular quantum mechanical system. So how to identify that? So first of all, we have to find, we must define a wave function which is in form of a complex function similar to a plus ib. So that if our a plus ib is existing, then obviously psi star a minus ib will also complex conjugate, that is psi star a minus ib will also exist, so that the total product of psi star a square plus b square will exist. So that you find the probability density. So probability density psi star psi, and within that integral, within that boundary, that is integral a to b psi star psi d tau value. Identify the value, calculate the value. If you get the value as 1, then you can conclude that the particle exists within the boundary. And if you calculated the value of psi star psi, that is probability density within the integral a to b, and you got psi star psi d2 is equal to 0, then you can conclude that the particle does not exist within that boundary. Okay, so you have considered a quantum mechanical system within a boundary from A to B, and you have defined a wave function psi, which is a complex function. And now if you find the probability density, that is integral A to B psi star psi d2, and you come across with value 0, this suggests that particle does not exist in the boundary. Or if you come across with the probability density value is 1, then you can confirm that the particle exists within the boundary. So this may or may not be happens, isn't it? But if the probability density within the space, that is integral minus infinity to plus infinity psi star psi d2, if you calculate that value, it should get 1. That means the particle exists within the space, and this is called as a normalization condition. Okay, remember these there are 2 points we have to remember clearly. For any defined wave function, you have chosen a quantum mechanical system, and you supposed to have a particle within that quantum mechanical system, and you are defining the wave nature of that particle within that quantum mechanical system with a wave function psi, so that you will come across with 2 things. One is, if you have defined your wave function such that within the boundary the probability of finding a particle is not, that is integral A to B psi star psi d2, may or may not be 1. What means that? Means particle may exist in the boundary or may not exist in the boundary, but the normalization condition must be satisfied. That means if you define psi value, if you have assumed psi value of any quantum mechanical system, if such that the normalization condition must be satisfied, whether within the boundary may or may not exist, that is secondary, but the normalization condition must be gets satisfied. Then only we can say that the particle is or that wave function what you have defined for that particle in a quantum mechanical system is valid. If it does not satisfying the normalization condition, you must change your wave function. Okay. So, and few more points to be considered for defining a wave function. Psi must be finite. That means if you calculate the probability density value, which is given by minus integral minus infinity to plus infinity psi star psi d2 like that, isn't it? So the probability density value, isn't it, will never be equal to infinite. That means you should not get the probability density value as infinite. You must get any finite value. That may be 0, not a problem, isn't it? 0 to any value, but infinite is not. You should not get infinite. Okay, so that is what the psi must be a finite value, and the wave function psi must be a single value. That means you should not have more than one value at a point in space. So this is representation for Heisenberg uncertainty principle, isn't it? So see, it should have a single value. So the psi should not have 2 values at the same instant of time. That is not possible. Okay, and it should be continuous. That means if you have if you can able to plot the wave function, isn't it, diagrammatically or graphically, then that particular wave function should has a continuous curve, but it should not have any breaks. If it is getting any breaks, means your wave function is wrong, and it should contain the first order derivatives. That means dou psi by dou x, dou psi by dou y, dou psi by dou z must exist. Okay, and very important thing is the wave function must satisfy the normalization condition. Okay, so I repeat once again, you have an quantum mechanical system and you assumed that there exists a particle within that quantum mechanical system, and if you want to know the behavior of the particle within that quantum mechanical system, then mathematically you have to identify, isn't it, how the particle is behaving in that particular quantum mechanical system. So for that purpose, we'll represent the wave nature associated with that particle in the quantum mechanical system, and that is mathematically defined as a wave function. So wave function is in general is represented in terms of a complex function. So you have psi with you, which is a complex function. Now how the psi should be, what you have defined psi, that is wave function. So anything can be considered as your wave function? No, it must satisfy some conditions. First one is the psi what you have chosen must be finite. That means by calculating the probability density value, it should get any finite value, but it should not get any infinite value. And second one, psi must be single valued. That means at any instant of time it should have only one value only, isn't it? And it should be continuous. So if you plot the psi value, it should be a continuous graph, isn't it? It should not have any breaks in that. And the first order derivatives of psi must exist. You have defined the psi which is equal to some complex function, and if it is not having any first order derivatives, then it is useless. So it should have a first order derivatives, and most important is it must satisfy the normalization condition. So normalization condition means you take that psi what you have defined and you place it here, isn't it, in minus infinity to plus infinity, psi star psi d tau, and you must get the value 1. If you get this value as 1, that means your wave function psi what you have defined is correct. Even if in the minus infinity to plus infinity psi star psi d tau, substituting in this value also, if you are getting the psi the value as 0, that means your wave function is not correct. Okay, so you have to rethink about the wave function. So this is about this physical significance of a wave function. Very important isn't it, concept to describe any quantum mechanical system. So mathematically it is a wave function is a mathematical term which defines the quantum mechanical system or particle behavior in a quantum mechanical system. Okay, so we'll come across with the next further things in the next class. Thank you.